Welcome back. In the last session, I think we saw classroom work problems. We solved up to 16 problems. Okay. Now I can say concept, multivibrators. Okay. Now don't write anything. The first one, a stable multivibrator. Okay. What out maybe you treat this as Opamp problem or Opamp application. The circuit is, let us say you can take it as an example, or this is what it is, minus, plus, and this is what is having a resistor in the feedback, and this is V0, and there is a capacitor which is what is connected here, C, and there's a feedback. Let us say this is R1, this is R2. Okay, and initially voltage across the capacitor is 0, and let us say this is what is R. Okay, let's see what is output voltage. Okay, if you treat this as a problem, right, then I'm asking you what is output. Okay, write the circuit, then we will see what is output. Now we need to find output. If you ask me where is input, there is no input. Then I'm asking you what is output, right? Let's see what is output. Write down. Let us assume that the initial voltage across the capacitor is 0. Let us assume that initial voltage across the capacitor is 0. Let us assume that initial voltage across the capacitor is 0. And it is defined with power supply. Let us say this is what is VCC. Maybe for your understanding, let me take VCC is equal to 10 volts. And this is minus VCC is equal to minus 10 volts. Okay, let's see what is V0. Now see, if the voltage across the capacitor is 0, now what I want to do, I want to plot, just don't write, listen here. Okay, now this is what is time t. Now I want to plot voltage across the capacitor Vc, and I want to plot V0. Okay, and this is what is time axis, and I want to plot V0. Okay, let's see. Initially, what is voltage across the capacitor? 0. Okay, if initially voltage across the capacitor is 0, therefore this is nothing but 0 volt at a time t is equal to 0. This is nothing but voltage across the capacitor. Right? Now, Tell me, this is what is 0. Now, what type of feedback it is? If you treat this as op-amp problem, what type of feedback it is? Actually, it has both the feedbacks. It has both the feedbacks. It has negative feedback and it has positive feedback. And I told how to find the type of feedback. If both the feedbacks are there, how to find the type of feedback? Out of these two feedbacks, if negative feedback is dominating, then overall it is negative feedback. If positive feedback is dominating, overall it is positive feedback. Right? Therefore, how to find that? I told you the technique. The technique is open the loop. Excuse me. When you open the loop, right, then if you increase the voltage, let us say I am increasing the voltage here like a step. Excuse me. When I increase the voltage like a step, right, within time t is equal to 0, right, within delta t, where delta t is equal to 0, means instantaneously I am changing the voltage. Now let's see. Earlier I told that 100%, out of 100% how much is the change, how much is the change. Now I am incorporating time also. Without time I cannot explain this. Okay, let's see. When output is changing suddenly, voltage across the capacitor cannot change instantaneously. Then what is the change here? The change is not there. Therefore, the change here is 0. There is no change. Voltage across the capacitor cannot change instantaneously. The change is 0. The change is 0. Now, what about this? This is R2 by R1. If there is a change here, then definitely R2 divided by R1 plus R2. That is nothing but beta network. Then beta times of the change you will get here. What that may be, here also you will see some change. But that is nothing but beta into V0. There is a change. But here there is no change. Therefore, tell me, if output is changing suddenly, then the voltage at plus is also increasing. But the voltage at minus is not changing because voltage across the capacitor cannot change instantaneously. Therefore, the change is 0. But here the voltage at plus is changing. Then this is increasing. When plus is increasing, then what about output voltage? This is also increasing. Therefore, when this V0 is increasing, this is also increasing. Both are increasing. When both are increasing, what is this feedback? This is nothing but positive feedback. This is nothing but positive feedback. If op-amp is in positive feedback, once you know that op-amp is in positive feedback, once op-amp is in positive feedback, then immediately comparator. The circuit is nothing but comparator. We should not use virtual ground concept. We should not use virtual ground concept. That is what we need to use. Okay. Don't disturb the original circuit. You write how to get or open the loop to find the feedback. That is what you say, and then finally it is positive feedback and comparator. Take it. Therefore, we got to know that it is a comparator. If it is a comparator, what is the next step? We have to take V0 voltage either plus VCC or minus VCC. Anything is fine. Okay. Then we will solve the problem. What is beta here? When you treat this as beta and then beta V0, what is beta? Beta is nothing but R2 divided by R1 plus R2. You draw separately. Don't disturb the original circuit. Okay. Again, I'll go back, but you have to draw. What is the heading for this? To find feedback. Over? Done. Now let me go back to original circuit. Okay. Now we know that if it is in positive feedback, we have to start with one of the output voltages. Let us say V0 is equal to plus VCC. When I say plus VCC, let us say 10 volt. And for your understanding, let me take R1 is equal to 1 kilo ohm and R2 is equal to 1 kilo ohm. But beta is R2 by R1 plus R2. Then tell me what is this voltage? Now this is nothing but beta into, when V0 is equal to VCC. Therefore, what is beta into V0? Beta into V0 is nothing but 1K, 1K, 10. Therefore, this is 5 volt. This is 5 volt. Okay. Now this is what, but that is what is case 1. You have to write like case 1. Then V0 is equal to VCC. Case 1 and V0 is equal to CC, which is equal to 10 volts. Then beta V0 is equal to 5 volt. Okay. Now let's see. Beta is nothing but R2 divided by R1 plus R2. Okay. Now tell me, when V0 is equal to plus 10, your beta V0 is equal to 5 volt, but voltage across the capacitor is 0. Therefore, plus is at 5 and then minus voltage is nothing but 0. Which is more? Because it is a comparator. And this is what is more? Because this is comparator. Therefore, plus is more than minus. When plus is more than minus, your output is plus 10. That is fine. Therefore, now tell me, this is nothing but RC circuit. Initially, voltage across the capacitor is 0, but your capacitor starts charging towards VCC because it is nothing but RC circuit, right? When capacitor starts charging VCC, when output is at VCC, it is trying to charge to VCC, but once this voltage crosses beta V0 or beta VCC, this is nothing but your beta VCC. Once it crosses beta VCC, then which is nothing but 5 volt, once this crosses 5 volt, then minus is more than plus. Then your output voltage will switch from plus 10 to minus 10. That is what I am plotting here, trying to plot here. Therefore, your capacitor is trying to charge to what? Your capacitor is trying to charge to plus VCC, right? But once it crosses, it is trying to charge to plus VCC. It is trying to cross to charge to plus VCC. That is what is trying to charge to plus VCC exponentially. But once it crosses, because this voltage is increasing, but once it crosses beta VCC or 5 volt, then minus is more than plus. Then once it crosses, let us say this is what is our beta VCC. This is what is beta VCC. What is beta VCC? Let us say 5 volt. Then once it crosses, your output voltage will switch from. This timing diagram is very important. This is what is easy to understand. Okay. Right? Then what is your output? Output is 10 or VCC. Right? Once your capacitor voltage crosses beta VCC, once the capacitor voltage crosses beta VCC, which is 5, then minus is more, then output will switch from plus 10 to minus 10. Therefore, it will become minus VCC, which is nothing but minus 10 volts. And this is 0. Right? Therefore, now tell me, when output is switching from plus 10 to minus 10, when output is becoming plus 10 to minus 10, then tell me what will be your beta VCC? Then your this will become minus beta VCC. This will become minus beta VCC, which is minus 5. Then tell me what is the voltage here? Now it went to what? 5 volt at time something, at a time t1. Let us say at a time t1. Therefore, this is what is becoming, once it crosses 5 volt, this is what is the time t1, this is what the time t is equal to 0. This is what is time t is equal to 0. This is also time t is equal to 0. This is what it is changing. Therefore, now tell me, now it is minus 5, but voltage across the capacitor is 5. Then your input is now minus 10. Your capacitor is trying to charge to minus 10. Your capacitor is trying to charge to minus 10. Let us say this is minus VCC. Your capacitor is trying to charge to minus 10. But once it crosses minus 5, it is trying to charge to minus VCC or minus 10. But once it crosses minus 5, minus 5.01, then minus 5 is more than minus 5.1, then your output voltage will switch from minus 10 to plus 10. Therefore, if I continue, right, I can say, let us say this is what is minus beta VCC, which is nothing but minus 5 volt. Then once it crosses, right, then again the output voltage will switch from minus 10 to plus 10, because it is a comparator. Then it will change from this point to this point. Again, output is plus 10. Again, this will become plus 5. But this is at minus 5. Again, this is what is trying to charge from minus 5 to plus 10 volts. Therefore, it is trying to charge to minus 5 to plus 10 volt. It is trying to charge. But you know, once it crosses 5, therefore it will toggle in between. Enough. Okay. Therefore, whenever it is charging, your output will be plus 10. Whenever this is discharging, your output will be minus 10. Again, whenever it is charging, therefore, if you see, this is what you get. Okay. Therefore, if you observe clearly, we can ignore first half cycle or first cycle. Right? You can start this as new time axis. When you start this as new time axis, this is what, let us say, new time t. Therefore, t dash, what it may be. Therefore, now t dash is equal to 0. Okay? That is what your new time axis. Therefore, this is what is repeated continuously, the voltage across the capacitor. Because we are starting 0, because initially voltage across the capacitor is 0. That's why normally if it is associated with some initial voltage 0 or whatever it may be, it's better to ignore first half cycle or first full cycle. Then we can see the repeated periodic waveform, that is what is from minus beta VCC to plus beta VCC, plus beta VCC to minus beta VCC. This is what is toggling in between, but you are getting ultimate output square wave. This is what is called astable multivibrator or square wave generator. Why it is called astable multivibrator? Once your output is plus VCC, after some time it is becoming minus VCC. After some time it is becoming VCC. After some time it is becoming minus VCC. When you say logic 1 is nothing but VCC and logic 0 is nothing but minus VCC, the logic 1, whatever you are getting at the output, that is not stable. Again it is becoming logic 0. Whatever logic 0 you are getting, that is not stable. It is becoming logic 1. Whenever you are getting logic 1, again it is becoming logic 0. Therefore, both these states, logic 1, logic 0, both these states are not stable. Both are unstable. Therefore, both these states are unstable or unstable. Therefore, multiple times it is vibrating between 1 to 0, 0 to 1, 1 to 0, 0 to 1. Therefore, astable multivibrator, or I can say square wave generator. When I say square wave, 1 0, 1 0, 1 0, without any input we are getting output. Therefore, the states are changing continuously, they are toggling continuously. Therefore, this is called square wave generator or astable multivibrator. I hope this is clear. Okay. Now we need to derive what is the time period. Therefore, this is what is our, let us say this is what is t dash is equal to 0 and this is what is t by 2 and this is what is the time t and this is what is going to give you the time period t, the total time t of your square wave. That is what we need to find. But if you observe clearly, if you find t by 2, that is enough. Into 2 you will get total time period. Therefore, if you find the time it takes, the capacitor takes to charge to beta VCC from minus beta VCC, problem is over. Problem is over. Draw the waveforms. Then once you understand the waveforms, we need to derive what is the time, how much time it is taking to get t by 2 or how much time it is taking to charge to beta VCC from minus beta VCC. Then we will see that. Okay, that is easy, straightforward. Once you understand the graph and then what is happening to the output and then why we are having the switching from one point to another point, then concept is done. Then mathematical analysis is straightforward. Okay, take it. This is what is the time t is equal to 0. Now this is what is time t1. This is what is time t1. And this is 0. And that's happening. The same thing is continued. Okay. See, this is self-explanatory. Okay. When output voltage is changing from plus 10 to minus 10, your capacitor is trying to charge to that minus 10. Again, once it crosses something which is the trigger point, again your output plus minus 10 is becoming plus 10. Again, if it is plus 10, capacitor is trying to charge to that 10. Again, this is what is becoming 5. Once it crosses 5, again output is changing. Right? Capacitor is trying to track the output, but it is triggering your output. Again, capacitor is trying to track your output, but again it is triggering your output. Therefore, continuously it is happening. This is nothing but square wave generator. If you understand the timing diagram, for both VC, voltage across the capacitor, and output voltage, I think you understood. Now let's see the derivation part. Okay. Now listen, I will give you time later to write down. Therefore, tell me, if you take voltage across the capacitor, what is voltage across the capacitor formula? we know that voltage across the capacitor Vc is equal to V final plus V initial minus V final into e to the power of minus t by tau. Don't say Vc is equal to Vcc into 1 minus e to the power minus t by tau, that is for charging. That is not always true. That is true if the capacitor initial voltage is 0. This is 0, but I told, right, initial voltage is 0, but we are ignoring first half cycle. Now you have to take new time axis. New time axis in nothing but this is what is my new time, t dash is equal to 0. At that time, what is initial voltage? Minus beta Vcc, right? Then it is trying to charge to your Vcc. But something is happening, something is triggered, your output is changing suddenly. Once it crosses your beta Vcc, then your capacitor is trying to charge to minus Vcc. Therefore, this is what is continuing. This is what is the capacitor, okay? Now, time, now new time, right? What it may be. Therefore, now, that is new time, therefore, t, and let's say t dash, what it may be. Then 0 less than or equal to t dash less than or equal to t by 2. In between 0 to t by 2. Then tell me what is your initial voltage? What is your initial voltage? From here to here, what is initial voltage? Your capacitor is starting from minus beta Vcc. Minus beta Vcc. And what is final voltage? Final voltage means the voltage what it is trying to charge. Don't say beta Vcc. That is not final voltage. The final voltage what it is trying to charge is nothing but Vcc. But something is happening in between. It is triggering to see the change in output voltage because it is a comparator. Once the voltage at minus is changing, then output is changing. But your capacitor is trying to charge to Vcc only. It is trying to charge to Vcc only. That is what is the final voltage. But something is happening at some time. That is nothing but a time t dash is equal to t by 2. The voltage across the capacitor is beta Vcc. That is what we need to find. But it is trying to charge to Vcc. That is what is called forced voltage or final voltage. Therefore, what is final voltage? Final voltage is Vcc. I think people will be confused here. Final voltage means they will think that beta Vcc. That is not final voltage. Final voltage is nothing but the forced voltage or drive voltage. That is Vcc. But at time t dash is equal to t by 2, that will be the voltage across the capacitor will be beta Vcc. That is what we substitute to get t dash, which is t by 2. Okay, that's fine. You substitute, then you'll get the equation. Therefore, this is what your star. Let me rub one space. Okay. So for now, tell me, star implies voltage across the capacitor Vc is equal to V final Vcc plus initial minus beta Vcc and minus V final minus Vcc into e to the power of minus t dash divided by Rc. What is tau? Tau is nothing but time constant of your capacitor circuit. That is nothing but Rc. Then this is nothing but if you take Vcc common minus Vcc common, you will get 1 plus beta into e to the power of minus t dash divided by Rc. This is what is voltage across the capacitor. Now we know that at a time t dash, the time t dash is equal to t by 2. At a time t dash is equal to t by 2. What is voltage across the capacitor? Voltage across the capacitor is equal to beta into Vcc. Therefore, what is Vcc? Beta into Vcc is equal to Vcc minus Vcc into 1 plus beta into e to the power of what is t dash? T by 2. Therefore, minus t by 2 Rc. Therefore, Vcc, everything will be cancelled. Then if you take this side, you will get 1 plus beta into e to the power of minus t by 2 Rc is equal to 1 minus beta. Then if you take this side and then natural logarithm, minus t by 2 Rc is equal to ln 1 minus beta divided by 1 plus beta. Then if I take this Rc and then 2 and then minus inside, t will be equal to 2 into Rc ln, this minus if I take inside, it will be 1 by a. 1 plus beta minus 1 minus beta. This is what is the time period of your square wave. and frequency of your oscillations, square wave oscillations, is equal to f is equal to 1 by t. Square wave repetition, okay, which is nothing but what? 2 RC ln 1 plus beta divided by 1 minus beta. What is beta? Beta is nothing but R2 divided by R1 plus R2. That is what is your beta. How much you are sampling and then feeding at the positive terminal. That is what is your beta. And this is what is the time period of your square wave. Straightforward. Okay. Take it. Maybe if you take the same thing, T by 2 to T, initial voltage will be beta VCC, final voltage will be minus VCC. If you calculate again, you will get the same. Whatever this is T by 2, then into 2 you will get total time T, because this time is equal to this time. Therefore, your square wave is having 50% duty cycle, means on time is equal to off time. 50% of total period is nothing but your on time, 50% of total period is nothing but your off time. Okay. If you give the square wave to integrator, what you get? Triangular wave. Therefore, whatever you want, you can get it. Square wave, we can get it. Triangular wave, we can get it. Sawtooth waveform also, we can get it. That we will see from 555 timer. Okay. Whatever type of waveform you want, we can get it. Sine wave. How to get sine wave? That we see after this. After multivibrators, I'll explain oscillators. Sinusoidal oscillators. The circuit which satisfies Barkhausen criteria, that will be giving you sinusoidal oscillations. That we will see. Okay. Therefore, you know how to get sine wave, you know how to get square wave, you know how to get triangular wave, you know how to get sawtooth waveform. Therefore, enough. If this is over, then we can go to next circuit, monostable multivibrator. Okay. I'll give you 1 more minute time. Try to complete in a minute. But before explaining monostable multivibrator, we want something called trigger circuit that we will see. Okay. Now the second one, monostable multivibrator. Okay, now before that, write down trigger generator. Ideally people call it as impulse generator, trigger or impulse generator. Circuit. Okay, just listen. Now if you take if you want impulse or trigger, right, we want spikes, therefore differentiator. What is differentiator? If you take differentiator circuit, this is R and this is your Vi of t, input signal Vi of t. Therefore now tell me, if I give square wave, right, what you get? This is what your Vi of t, right? Then this is what is t, then t by 2 and then t. Then where, if you want to get RC is very much less than t by 2. Then tell me what you get. Then I am asking you to get, let us say, if I take a forward bias PN junction diode, then tell me what is V naught of t. What is V naught of t? We know that. Just tell me what is output here. Let us say this is what is V naught dash of t. Then what is V naught dash of t? Then if you ask me V naught dash of t, or directly I can give you V naught of t. Okay, or V naught dash of t, right? This is what your time. Tell me what your input. Your input is square wave. Then what is your output? Your output is nothing but, this is nothing but V naught dash of t. This is V naught dash of t. Tell me what is your output. You will get a trigger, but you have to ignore the first cycle. Then we shall get two types of pulse. This is what you will get, right? This is what your output. But when you pass it through PN junction diode, forward bias PN junction diode, it passes only positive triggers and it will not pass negative triggers, right? Then what is V naught of t? Your V naught of t will be, therefore, okay. Now tell me what is your output. Your output will be only positive triggers. Why? This is what is your V naught of t. This is what is your V naught of t. Why? It passes only positive triggers, it will not pass negative triggers. For the negative trigger, this PN junction diode will be in reverse bias. Therefore, it passes only positive triggers. Therefore, this is what is our trigger or impulse generator circuit. Now, if you take PN junction diode opposite to it, then it passes only negative triggers. Okay, that you can take it as homework. Okay, take this circuit. We are going to use this circuit, not this. With wherever you want positive trigger, you can apply like this. Wherever you want negative trigger, just change the direction of your PN junction diode, you will get negative triggers. Okay, that is homework for you, which you have to do. Okay, that's fine. You have to ignore first half cycle or first full cycle, because here if you take it as time t is equal to 0, it is starting from 0 to V, but practically minus V2 plus V. Therefore, there is a 2V delta change. But the triggers will have 4V peak to peak. Therefore, this is what is case 1, positive trigger generator. Now case 2, homework, negative trigger generator or negative impulse generator. Anything is fine. But practically it is a trigger, not impulse. Impulse means having very high amplitude and area is equal to 1. Area under the impulse is 1. But it is not impulse, ideal impulse. That's why I am saying it as trigger circuit. Okay. Now the same signal, same square wave, but now this is what is your p-n junction layer. Now I am asking what is V0 of t, and this is V0 dash of t, this is C, this is R. If you give the same square wave, but the condition should be what? The condition of this circuit will be R should be very much less than t by 2. Then only it will give you triggers, else it will not give you triggers. Okay. Then tell me what is V0 of t. V0 dash of t, both are same only, but V0 of t will be only it passes negative triggers. Directly you can get it. Therefore, what is V0 of t? Your V0 of t will be equal to this is your V0 of t, right? It passes only negative triggers. Okay. This is what is continued. Remember, when you say this is V minus V, it will be 2V, it will be minus 2V. That is what. Therefore, whatever negative peak you have, negative value, negative square wave value, you will get minus 2 times. 2 times of that negative value you will see in the trigger. Okay. Basically, this is differentiator, passive differentiator. Wherever you want triggers, right, to change the state, okay, because one of the states of monostable multivibrator is stable, we need to disturb that state, then it will enter into another state. If that state is not stable and it is coming back to stable state, we have to disturb this state, okay, then we will apply it either negative trigger or positive trigger. And the third circuit, bistable, we need to apply both negative trigger as well as positive trigger to disturb the states of the circuit, then it will come to one of the stable states. Every time we need to disturb the state to change the state, okay. Then we need to apply both positive trigger as well as negative trigger. In that case, what we do, we will directly apply positive trigger as well as negative trigger with the 2 p-n junction diodes, and directly we can give the output, okay. That is what we can say. Case 3, positive and negative triggers, right? You may say this is another positive and negative trigger, but we don't want to load your RC circuit. Then what people do, people will take this circuit and then reverse bias p-n junction diode and then will add it, right? Therefore, positive and negative trigger circuit. Then capacitor, resistor, p-n junction diode, capacitor, resistor, reverse bias p-n junction diode, both we can add, and then you can call this as V0 of t. For both you can give Va of t. This is Va of t, this is also Va of t, you can short. For both you can give square wave. This is what is your Va of t. C R C R. You may say, why don't we take directly the RC circuit, right? If you take RC circuit, yes, you get positive trigger, negative trigger. I agree, but if you take this, we have 0 volt also. We don't want 0 volt, we don't want 0 volt to be forced onto some other circuitry. We want, whenever I want trigger, then only the circuit should come into picture. If you don't want trigger, the diode should be reverse bias or off. If diode is off, then this voltage will be floating. That voltage will be decided by some other circuitry. We don't want to force that node always to 0 if you use directly simply RC circuit. That is the reason why we are adding 2 PN junction diodes. This node should be driven, this node voltage will be driven by some other circuitry. Then that node voltage should not be returned by your RC circuit. If you take only RC circuit, even though you want positive and negative trigger, the voltage, output voltage will be 0, which is forcing that node to 0 always. No. Whenever I want trigger, positive trigger and negative trigger, these two circuits will come into picture. Now if you plot V0 of t, you will get both positive as well as negative trigger, same as this, but isolating circuit. It is independent of the load what we have. It will just force the triggers. Okay. Time is over. Now we will continue in the next session. If you want, you can take it as homework and then you can find what is V0 of t. Okay. Thank you.